Welcome to another deep dive into the online encyclopedia of integer sequences.
Hello.
For those following our series, especially number theory students, we're continuing our journey. And today we're hitting OEIS A000198.
Yes, A000198. It's listed as the number of automorphisms of tournaments with n-labeled vertices.
Sounds pretty specific.
It is, but it's a fantastic meeting point for group theory, graph theory, and combinatorics, all really core areas.
Okay, let's unpack that. First off, tournament. What are we picturing mathematically? Is it like a sports bracket?
Sort of, yeah. Think of a round-robin tournament. Everybody plays everybody else exactly once.
Okay.
So mathematically, it's a directed graph. Between any two distinct points or vertices, there is exactly one edge, and it has a direction, like player A beat player B, so the arrow goes A to B.
Got it. So it's like taking a complete graph where everything's connected and then deciding a direction for every single edge.
Exactly that. An orientation of a complete graph.
So our mission today is to understand what an automorphism of this structure is and what this sequence, A000198, is actually counting.
Precisely. And to do that, maybe we should quickly recap graph automorphisms in general.
Good idea. So an automorphism of a plain old graph, it's a way to shuffle the vertices around, right?
A permutation of the vertices.
Yeah.
But the key thing is it has to preserve the structure.
Meaning if two vertices were connected by an edge before the shuffle, they still have to be connected after.
Yes, and just as importantly, if they weren't connected, they still aren't connected afterwards.
Yeah.
It preserves both adjacency and non-adjacency. That's roughly definition 2.2 in one of the graph theory sources.
Right, it's like relabeling the points without changing the actual diagram.
Exactly. And importantly, all the possible shuffles, these automorphisms, they actually form a group if you combine them. You do one shuffle, then another. That combination is also a valid shuffle. That's the automorphism group, AUG.
Okay, that makes sense. It's a set of symmetries.
And there's a neat little property mentioned, theorem 2.4, I think it was, a graph and its complement, where you swap all edges, and non-edges have the exact same automorphism group. AUG equals AUG bar.
Interesting. So the symmetries are the same whether you focus on connections or non-connections.
Yep.
So how does this apply to tournaments then? We have directions now that must change things.
It does. It adds a constraint. For a tournament, an automorphism isn't just preserving connection. It has to preserve the direction of that connection.
Okay. So if vertex points to vertex V, meaning you beat V.
Then after you apply the automorphism, the vertex that you landed on must still point to the vertex that V landed on.
The win-loss outcome for every single pair has to be maintained after the relabeling.
Precisely. So you relabel the players, but the results of all the games look exactly the same relative to the new labels.
Which brings us back to A000198. So A000198 is the count of these direction-preserving relabelings for a tournament with n-labeled vertices.
That's the one. It's counting the number of elements in the automorphism group for that specific tournament.
Let's look at the numbers. The sequence starts 1, 1, 3, 3, 5, 9, 22, 59. Then 167, 490, 1486. Wow, it grows really fast.
It does, doesn't it? It shoots up pretty quickly.
What does that rapid growth suggest about tournaments?
Well, it hints that as you add more vertices, the potential for these kinds of symmetries, it increases quite significantly. Even though the number of possible tournaments itself grows astronomically, the number that possess some non-trivial symmetry also grows quite fast. It reflects, I suppose, an increasing structural complexity.
Now, you mentioned groups. How does this relate to permutation groups, like the big one, SN?
Right, so Sn, the symmetric group on n elements, contains all possible permutations, all n factorial ways to rearrange n items.
Okay.
And the automorphism group of any graph on n vertices, tournament or not, is always going to be a subgroup of Sn. It's a subset of those permutations that happen to preserve the graph structure.
And for some graphs, like the complete graph K, where everyone's connected to everyone with no direction, the automorphism group IS the entire Sn.
Right, exactly. Because if every pair is connected, any permutation preserves that universal connectivity. Any shuffle works. That's theorem 4.1 mentioned in the source.
But for tournaments, the directionality really cuts down the possibilities.
Massively. That direction constraint is strict. You go from n factorial potential symmetries down to the numbers in A00000198, which are much, much smaller than n factorial quite quickly.
So actually finding that number, A00000198, must be hard work.
Oh, it's a challenging problem in combinatorial enumeration. There's no simple plug-and-chug formula for A000198n.
No neat expression.
Not that we know of. What we do have, as mentioned in the sources, are recursive formulas, ways to calculate a term based on previous terms.
Like the ones in MapPLE or Python code snippets shown in the OEIS entry?
Exactly. Those often come from research papers, like the reference to Alspach and Berggren from the 70s. They found ways to build up the count. It lets us compute the sequence, but it doesn't give that, elegant, closed form.
It really speaks to the complexity. You can't just write down a formula, you have to build it up step by step.
It does. It suggests the structure of tournament symmetries isn't easily captured by a simple pattern.
Okay, let's pivot slightly. For the number theory students listening, why should they be interested in the symmetries of these directed graphs? What's the connection?
That's a great question. The core connection is group theory.
The study of symmetry itself.
Precisely. And group theory is absolutely fundamental in number theory. Think about Galois theory, understanding solutions to polynomials through groups. Or representation theory, which connects groups to linear algebra. Emmy Noether's work, mentioned in some of the background reading, was foundational here, linking abstract algebra to physics and other areas. These algebraic tools developed for number theory and abstract algebra are exactly what we use to analyze the symmetries of combinatorial objects like tournaments.
So understanding Aught-G for a tournament uses the same kind of mathematical machinery group theory that's central to number theory.
Absolutely. It's applying those powerful abstract concepts to a concrete combinatorial setting. It shows the unifying power of these mathematical ideas. Studying these automorphism groups gives you insights into the structure, the invariance, the properties of these objects, using tools you're likely already familiar with from algebra and number theory.
It's like seeing the same language used to describe different phenomena.
A perfect analogy.
Okay, so let's try and wrap up this deep dive on A000198. We've established it counts the number of ways to relabel vertices in a tournament while preserving all of the win-loss direction.
Or just the size of the tournament's automorphism group.
And finding this number isn't straightforward. There's no simple formula highlighting the complexity, but we can compute it recursively.
And the study itself is a great example of group theory applied to combinatorics.
Absolutely. I definitely encourage listeners to check out the OEIS entry for A000198, maybe chase down some references like Alspach and Berggren, and just think about how automorphisms pop up elsewhere.
Definitely. And maybe a final thought to leave people with. How might the nature of the automorphism group relate to other properties of the tournament?
What do you mean?
Well, does a tournament with a very large, complex automorphism group behave differently from one with only the trivial symmetry? For instance, does it affect things like the number of Hamiltonian paths or cycles or the score sequence?
Ah, so could the symmetries predict or correlate with other structural features?
Perhaps. It's an active area. How does the algebraic symmetry manifest in the combinatorial properties? That's a deep question.
Something to chew on. Excellent. Well, thank you for that exploration. Join us next time as we pick another sequence from the incredible OEIS.